All right, let's dive right in. If you've spent any time with physics, you've definitely heard of the legendary I.E. Irodov problem book. It's notorious for its tough problems that really make you think. And today, we're going to tackle one of its classics, problem 1.51. But before we even look at the problem, let's start with a simpler idea. Picture a wheel or a disk rolling on the ground. At any single snapshot in time, is there a point on that disk that isn't moving at all? I mean, completely, totally still. It's a bit of a brain teaser, right? The top is whipping forward, the center is moving steadily, but what about the very bottom point, the one touching the ground? That idea right there is the key to this entire problem. Okay, here it is, the official problem statement from the book. Irodov wants us to find the equation for the path of that still point we were just talking about. We need to find its height, y, as a function of its horizontal position, x. And he gives us two different scenarios to solve. First, in part A, the disk's center has a constant velocity, but its spin is speeding up. Then, for part B, the center is accelerating, but its spin rate is constant. So, to even begin to crack this, we need to get a solid handle on the physics behind that still point. It has a formal name, and it's called the instantaneous axis of rotation. We'll just call it the IAR for short. So, what is the IAR? Well, it's the exact point on a moving, spinning object that for a split second has a velocity of 0. You can think of it like a temporary pivot. For just that one instant, it's as if the entire disk is just rotating around that single point. It's an incredibly powerful concept that simplifies a lot of complex motion. So how do we find this magical point? Well, think about it like this. The velocity of any point on the disk is really a mix of two different things. First, you've got the whole disk moving forward. That's the translational velocity, VC. Second, you've got every point spinning around the center. That's the rotational velocity, vrot. The total velocity of any point is just the sum of those two vectors. And this brings us to the core condition for the IAR. It's that one special spot where the forward motion, VC, is perfectly exactly canceled out by the backward spinning motion, vrot. They have the same speed but are in opposite directions, so they add up to 0. And a point with 0 velocity is, well, at rest. Okay, with that physics locked in, we can come up with a step-by-step game plan. This is the exact roadmap we'll use for both parts of the problem. First, we'll write down equations for the center's velocity and the angular velocity based on time. Then we use our IAR condition to find its height, y. And the crucial trick is step 4. We get rid of the time variable, t, to get our final path, y of x. So let's put this plan into action. All right, time for case A. Remember, this is where the disk's center cruises along at a constant speed, but its rotation is speeding up. So what are the starting conditions here? They're pretty straightforward. The velocity of the center, VC, is just some constant, v. That means its position is simply x equals v times t. The angular velocity, omega, starts from rest and increases steadily. We write that as omega equals beta t, where beta is just the constant angular acceleration. Now we apply our core principle. The speed from rotation at some height y above the center is just omega times y. At the IAR, this has to be equal to the forward speed of the center, v. So we get v equals omega y. We just shuffle that around a little bit and we find the height of the IAR. Y equals v divided by omega. Simple as that. Okay, but the problem asks for y as a function of x. Right now, our equation for y depends on omega, which depends on time t. We need to get rid of t. Luckily, we know that x equals v times t. We can easily rearrange that to solve for time. T equals x divided by v. The next step is pretty mechanical. We take our new expression for time, t equals x over v, and we plug it right into our equation for angular velocity, omega equals beta t. And just like that, we have omega described in terms of the position, x, instead of time. And here we are. The final step for case A. We go back to our IAR condition, y equals v over omega, and we substitute in that new expression for omega that we just figured out. And there it is, the final answer, y equals v squared divided by beta times x. And if you remember your math classes, that is the equation of a hyperbola. So the path of this still point is actually a hyperbola. How cool is that? Great. One down, one to go. Now let's tackle case B. We're going to use the exact same logic, just with a different set of starting conditions. So for case B, the rules are kind of flipped. Now, the center of the disk has a constant acceleration, w. This means its velocity is increasing with time, v equals w times t, and its position is given by that classic kinematics equation, x equals 1/2 wt squared. But this time, the angular velocity omega is just a constant. Now here's the beautiful part. Even though the motion is different, the fundamental physics hasn't changed at all. The IAR is still the point where the forward velocity v cancels out the rotational velocity omega. So our starting equation is exactly the same as before, y equals v divided by omega.
Just like last time, we need to eliminate t. This one takes a little more algebra, so let's walk through it together. We have two equations to work with. X equals 1/2 wt squared, and v equals wt. From the second one, we can say t equals v over w. Now, if we substitute that into the first equation, we get x equals 1/2 w times the quantity v over w squared. After a little bit of cleanup, we find a really handy relationship. The velocity v is equal to the square root of 2wx. And now for the final substitution. We take our brand new expression for velocity, that v equals the square root of 2ewx, and we plug it into our trusty IAR equation, y equals v over omega, and that gives us the path for case B. And this time, if you look at the form, the equation describes a parabola. Same method, different motion, totally different path. Whew, all right, we've solved both parts. Now, let's take a step back and wrap this all up. And maybe more importantly, let's talk about the common mistakes people make on problems just like this one, so you can avoid them. Looking at them side by side really tells the story. In case A, we had constant forward speed, but an accelerating spin, and that gave us a hyperbolic path. In case B, we had an accelerating forward speed, but a constant spin, and that gave us a parabolic path. You can see how the final shape is a direct consequence of the relationship between the two types of motion. Now listen up, because here are the traps you need to watch out for. The number one mistake is mixing up your kinematic equations. Using x equals vt when you have acceleration is a classic error. Also, be really careful with your algebra when you're getting rid of t. It's super easy to make a small slip up there. And please, remember the IAR is where the total velocity is zero, not just one part of it. So what's the big takeaway from all this? The instantaneous axis of rotation isn't some fixed point on the disk, it's constantly moving. Its path is a beautiful mathematical description of the dance between an object's forward motion and its spin. If you can really grasp that concept, you're well on your way to mastering rigid body dynamics. So we found the path of the point with zero velocity. But what about a different point, like one right on the very edge of the disk? As the disk rolls, that point on the rim traces out a really famous curve called a cycloid. Now that you understand the IAR, how would you even start to figure out the equation for that path? That's a fantastic next-level challenge to really test your skills. Thanks for working through this with me, and I'll catch you on the next one.